Professor Peter Rowlands. His speech is on why do quarks have electric charge?
So I've set myself a very difficult question here. Why do quarks have electric charges? So let's look at the nature of fundamental particles. We have two types of fundamental particles. We have bosons, which have no weak charges, and that's why they're bosons, they collect together. Fermions, which have weak charges. So that separates the two basic classes of particles, so we know why they're different. Then the fermions divide into two. They divide into quarks with strong charges and leptons with no strong charges. So we know why they're different. But where does electric charge come into it? It doesn't. There's no obvious place for it there. It doesn't separate bosons, fermions, or quarks and leptons. Yet we see that there are quarks, there are no quarks that we know of without any electric charges. They've all got an electric charge. But there are leptons without electric charges. So there's no obvious reason why that should be so. These are the quarks, and the B is the baryon number, 3 quarks in a baryon, etc. So each one of those has got an electric charge in the conventional picture. However, if we look at leptons, we've got neutrinos without any, and ordinary charges, ordinary leptons with electric charges. So there's no obvious reason for that. It's got nothing to do with the strong interaction. Is there any good reason why we can't have 0 electric charge ones? Well, nobody's ever found any. And in particle physics, a very key point is that the strong interaction is not dependent on the electric charge in any way. These two interactions are completely separate, and there's a very fundamental reason for that, that the weak, strong and electric interactions have separate conservation laws. And we know that because we got baryon conservation, lepton conservation. If we put those two things together, we'll see that those two, along with ordinary charge conservation, we'll see that we've got 3 laws which determine the fact that all 3 charges are separate. They don't interact with each other. And yet, if we want to create a strong interaction system with quarks, we have to have electric charges. Why on earth isn't that the case? Well, at first, this would seem like a question without an answer. And if we just take the quark theory as a given, then we will never answer it. We've got to get somewhere deeper. And there is an answer, but we've got to go down deeper and deeper into the foundation level of physics. The deepest level that we can possibly reach, where fundamental symmetries determine things rather than mathematical equations. So the 3-dimensional or colour property of strong charge cannot be done without the presence of electric charge as well as the weak charge, and we will demonstrate that. But I have to start with an even more fundamental concept. And this is one that I've spoken about many times before. I can't discuss it in detail this time. I've spoken about it at other Vigier conferences and many other places, in many books and papers. This is a symmetry between the fundamental parameters space, time, mass and charge. And in my view, this is a Klein 4 or D2 symmetry, and we can represent it in a lot of different ways. And essentially, what we've got is 2 symmetries at the heart of this. We have 3-dimensionality or anti-commutativity, and we have duality or summation to 0. Essentially, the numbers 3 and 2 are the most fundamental in physics. And this is the way I see those concepts emerging. We've got 2 conserved quantities, 2 non-conserved, 2 real, 2 imaginary. We square one lot, we get minus, we square the other lot, we get plus. And then we've got dimensional quantities like charge. I'm assuming charge is what we call a three-dimensional quantity, the same as space. We've got others that are not dimensional. Commutative, anti-commutative, there's all kinds of ways of representing their opposition. And that's a nice diagram showing this structure. Now the important thing about that structure is that I first came across this structure, first worked it out more than 40 years ago. And I've spent 40 years trying to find a fault in it, and I cannot find one. And every time something seems to be an anomaly, then there comes an explanation which leads to a new piece of physics. So I'm pretty convinced that that is totally true. We can represent it in an algebraic way, if you like. It's one of many ways of representing it. And I can represent the properties algebraically, x's, y's, z's. I can represent it in diagrams. The books and papers have done show many of these representations. You can switch the pluses and minuses round. The symbols can be completely different, anything you want, but there are ways of doing it. We can also reduce the properties purely to algebra. Those properties are determined purely by algebra. And if we can reduce these properties purely to algebra, so we can reduce physics to algebra in this sense. Now, connecting with what Brian was saying, I don't think this is just physics. I also think that this leads on to biology, sort of partly bypassing chemistry, though chemistry can be done in the same way. Essentially, that there are patterns here which re-emerge in biology. And I've done a lot of work on that with my colleague Vanessa Hill. Did some on the last Vigier conference on that. So, if we want an ontological ordering, I call it a universal rewrite system, we can derive our algebra by a systematic process of extending it. We start off with scalar algebra, pseudo-scalar complex algebra for time. That gives us the connection we usually have in relativity. And then charge, which appears to be a quaternion structure, IJK, imaginary three-dimensional numbers, and space a vector structure. There's lots of different ways of ordering that. I could do it on epistemology instead of ontology. I could say that we do everything through space and everything else then follows. There are lots of different ways of doing it. And we can express the whole, if we have a vector algebra, then space also has areas, it also has volumes. Areas are pseudo-vectors. There's the first three symbols are vectors. The second three symbols are pseudo-vectors, which are the same mathematics as quaternions. Then we have pseudo-scalar for volume. This is standard Clifford algebra, and then unit for scalar. And so I can represent that space's properties by using vector, pseudo-vector, pseudo-scalar and scalar, or I can represent it using vector, quaternion, vector and pseudo-scalar and scalar. And charge, similarly, is like a subset of space, and so is time, and so is mass. So the other three properties other than space have algebras which were subsets of the main algebra. And if we put them together, if we put the three sub-algebras together, mathematically, they produce something that combines into being a vector algebra. So none of the three separately is a vector algebra, they're not big enough, but put them together and they are. And I've done that in red because I want to separate it from the actual space algebra, space vector algebra. Now, one of the aspects of this I mentioned earlier was summation to zero. I said there is a fundamental principle in nature in which nature cannot be characterized. It's got no bias, it's got no special characteristics, nothing like that. And I think that's got to be a fundamental principle. In a sense, this is a zero totality. Zero totality of concept as well as numbers. It's not just energy that adds up to zero, it's even the whole concept does. You've got to have no bias, no special restrictions on it. And in the group, we saw when I put those x's and y's, we could see it total to zero. And so one way of looking at that is to say that that combination there, with all the red stuff making up one other space, is like a kind of counter to the blue stuff, which is space as we understand it. We've got space and, if we like, an anti-space. Okay, like so. Let's just say that physics is contained within those algebras. And what do we do when we combine them? Well, let's put the 4 algebras side by side and let's work out the combinations of those. So let's work out the tensor product, or whatever you want to call it, that will produce all the algebra that those have. Well, that's what it looks like. When we've multiplied everything out, it looks like that. 64 terms, 32 plus and 32 minus, arranged in 12 lots of 5 and the 4 numbers 1i, etc. And that's just pure algebra. There's no magic in this, pure algebra. Well, that algebra is a magic algebra, because that is the algebra of the Dirac equation. The Dirac equation describes the fermion, the fundamental particle in nature. So, simply putting the algebras that respond to the fundamental parameters of physics gives us the algebra of the most fundamental concept in nature. And the concept in physics is that the fermion is a point particle. A point particle is 0 size. In a sense, we put 2 spaces together to create a point, because we cannot have a point in our space. In our space, there's no such thing as a point. Our space is rotation symmetric, translation symmetric. We cannot fix a point in it. But if we have 2 spaces, then we can. If one is counter to the other, to give us 0 totality. So we can have our 2 spaces in that form. This is the, as I mentioned, the combined algebra is equivalent to the gamma matrices of the Dirac equation. The algebra of the fermionic state. We don't know anything in physics other than fermions and their interactions. Bosons are simply products of fermion interactions. Everything comes from that. Now, a group doesn't need to be specified by all its elements. That's a group of order 64. You can just pick out some elements and it will give you the whole group. Here, the minimal number is 5. It's not 6. So, that's very nice and symmetrical, but that is not the minimum number. Nature will always go for the minimum for whatever reason. And we can choose a minimum by choosing any of those groups of 5. So the positive line at the top on the left, that 5. Those 5 are generators of the whole group, and so are any of those sets of 5. And this is the trick that we can use. Let's put the parameters, the algebras together, and then let's take the charge algebras and stick them on the other 3. And we get this more complicated structure. And those will generate the whole algebra. And they're more minimal than using the 2 lots of space. 2 lots of space is correct, perfectly symmetrical. But this is, we've broken the symmetry because we've gone for a more minimal construction. And what we've broken is the symmetry of that red structure. You can see the K, the I and the J are connected with separate things, whereas all the blue ones are symmetric. So we've broken the rotation symmetry of the red structure and kept the rotation symmetry of the blue structure. Now, space is a conserved quantity, a non-conserved quantity. And if it's a non-conserved quantity, we must retain its rotation symmetry, because that is a fundamental property of non-conserved. We can't pick out one axis rather than any other, because it's not conserved. However, charge is a conserved quantity, so we can break its axes. We can break the symmetry of its axes. And in fact, we must, because if we didn't, we wouldn't be able to pick out one from the other. They would be just like space. So, what we're doing here is showing how the 5 generators, minimal compared to 6, leads to the broken symmetry between the 3 charges. And this has troubled physics for all this time, ever since the Standard Model was first created in 1973. And we haven't got further than the Standard Model since it was created. We know from the Standard Model that there are SU2, SU3 and U1 symmetries for the 3 interactions. Well, here we see the beginning of it. There you see on the left you see the SU2 beginning. In the middle you see the SU3 beginning and the U leaving the U1 for the right-hand one. And that's how I would represent it. Each charge becomes different in its effect because of the thing it's associated with. So, we see that we can, let's do it in terms of spaces. We can also do it in terms of spaces as well as the vectors and quaternions. We can see the second space now adopt different characteristics. So one of our spaces is broken, the other one isn't. One of our spaces is observable because it is a space, the other is just a mathematical construct, and so it isn't a space. And let's look at see what we've done when we've created those connections. What we've got is three new quantities, if you like, because they're not any longer just time, space, mass, and they're not any longer just charge. We can say the new compound and quantized physical quantities, energy, momentum, and rest mass. And those symbols on the bottom line are simply scalar multiples that we will use. Let me put them above the algebraic operators, which specify what they are, and let me combine them, and then we get an object that looks like the bottom line there. We're packaging the whole information that those four quantities have, packaging one package. And what happens with that? Well, we multiply it by itself, so it becomes squared, and it becomes e squared minus p squared minus m squared, or if you want to put velocity of light in, it looks like the third equation down. So in effect, we're saying that the whole package of nature is just the square root of this equation, and that squares to 0. And if we want to do it in quantum terms, we can quantize the first bracket in the usual way, the way we've always done for the Schrödinger equation and so on, kd dt, and replace E with that, and P with del. That's just for a free particle, but we can do it for a bound particle as well. And we will get a quantized version of that equation. So what's happening with the quantized version is we're just talking about the most complete possible variations in space and time, because one of the fundamental aspects of space and time is that they're non-conserved quantities. So that's what the phase business is all about. Effectively, the operator is something that needs to be decoded to find the answer, and the answer is the second bracket. And so that if we include all possible signs of variation of E and P, because they're completely free as plus or minus values, we get 4 expressions, and those are versions of the Dirac equation for a free particle. Now, let me just separate out the 4 terms. What's the meaning of having 4 terms? This is the amplitude terms rather than the differential. It doesn't make any difference which we choose. If we look at after the first term, let's suppose that represents a Fermi electron or something, then the other 3 are the parity translation, the time translation, and the charge conjugation. So those are the 3 changed versions.
Did you mean time reversal?
Yes, I meant time reversal. Yes, not translation, reversal. Time reversal, parity reversal, and charge conjugation. So we can take the first bracket as the first thing, and the rest as those possible transformations. Now, if we square that object to 0, this gives us immediately Pauli exclusion, because no 2 particles can have the same bracket. They have the same bracket, psi 1, psi 2. If psi 1 equals psi 2, then the combination state will be 0. So we immediately got Pauli exclusion. So, if you like, fermions, you've got the Pythagorean addition for fermions adds up to 0. It is a point. It's a point in this dual space, if you like, and it couldn't be a point in our space because there's no point in our space, there's only points in this dual space. And interestingly, we define a point as the interaction between 2 spaces. We do that in the conventional Dirac equation. We assume that the point particle is switching between our space and vacuum all the time. Zitterbewegung, Schrödinger's solution of the Dirac equation for the free particle, produced this term Zitterbewegung, switching between them, which then led to the mass term of the equation. So we can't define a point without defining another space in which it exists and with which it interacts to produce the totality zero that we always want. And one space will necessarily appear distorted with respect to the other. It's only when we can lay them out side by side we can see that they got the same information. But on our normal viewing, one will be distorted. So let's go back to power exclusion for a minute. Nature totality is zero. So imagine creating a particle out of absolutely nothing at all. So if we create a particle with whatever potentials, whatever system it is, out of nothing, then we must leave in nothing the hole where that particle was, in effect, to retain zero. And that must be negative of it. And in physics, that means that particle and the rest of the universe with which it interacts. Total nothing. The rest of the universe is that hole in nothing that we've created, which we call vacuum. And if you like, both superposition states and combination states of fermion and vacuum become zero. And the vacuum for each particle must be different, which is another way of stating Pauli exclusion. Now, vacuum tells us where this other space is. I've already hinted at it because of the standard solution of the Dirac equation, the Schrödinger solution for the free particle. The other space, which is based on the charge objects, but includes the other parameters besides real space. And the fact that it's inaccessible is demonstrated by its chirality, by the fact that there's a chirality with respect to ordinary space, and also a chirality with respect to matter and antimatter, positive and negative energy, forward and backward directions in time. So the fermionic structure, why on earth does it do this? When we write down the fermion wave function, we write down 4. Why do we write down 4 and not 1? Well, it's because we need 2 plus E and 2 minus E. We need 2 in the other vacuum, in the vacuum space, in the other space. And 2 other time directions which we will never observe. So the universe will look like matter, but when we write down the Dirac equation, we're writing down antimatter at the same time. And where's that antimatter? Well, it's in the other space. It's over there. It's still there, but it's not observable. So that second space is the one that encompasses the rest of the universe, if you like. So the nilpotent, the squaring to 0, incorporates both on an equal basis. I'll not say anything about the Feynman things at this point. So the non-local aspect of the fermionic nilpotent, that's the local aspect, is the fermion. The non-local bit is the continuous vacuum, which is like the thing that counters it to 0. It seems that the continuous vacuum with its negative energy seems to be the same one as is associated with gravity, which is effectively a continuous process and not a discrete one. And we consider the fermion itself as in some sense being an inertial term, because it's the inertial, local inertial thing which counters the continuous vacuum gravitation, if you like. We can also use the operators which we identify with charges. We can play some mathematical tricks on them, and we can post-multiply our thing by k thing, and it doesn't make any difference, it's still the same. The k thing acts as a vacuum operator. And so does I and j if we choose to do those. But if we take, for example, the j on each side, well, let's take the I, that's easier. We will reverse the middle one. And so, in those 3 operations using the ki and j, we're reversing one of these objects. in the second bracket. It's easier to see it this way. Okay, if the first bracket stays the same, the second bracket changes the sign of something, and the third bracket stays the same. I'm only using one of the terms because it's complicated using 4. So, in effect, those 3 objects create those changes, those changed states. They create the vacuum states, if you like. And if we put them together, we will see that we have the first one changes the sign of the second bracket to -IKE, and if we combine those two, we get the wave function for a spin 1 boson. Spin 0 boson, paired fermion state, like Bose-Einstein's condensate or something. So we can see that the vacuum space is the one that's defined by the units connecting the charges. But we see that those units have many roles. They could be charges, PCT operators, dimensions of vacuum space, generators of the other 3 terms in the Dirac wave function, creation operators converting fermions to 3 types of boson. The complete vacuum can be the one defined by gravity or inertia, which the gauge force is split into 3-dimensional components. And we can also, I don't want to go into detail, but we can see that the total operator it conveys the angular momentum information about a particle state. The total information comes as angular momentum. And this, we can show how this introduces SU2, SU3 and U1. The idea I want to get over is that we can look at angular momentum either through the red operators or the blue ones. And the 2 spaces contain the same information about the whole of physics and especially about the angular momentum. Though in one it appears to be broken symmetry, in the others it doesn't. I'm now going to show that they're equivalent. If we want to know how a wave function maintains Pauli exclusion, we could know about its EP and N terms. In other words, we'd need to know the thing connected with the 3 red operators. Another fermion would have different things. We could plot them on 3 axes, 3 orthogonal axes, and then we could find a particular direction which would be unique to every fermion. But let's have a look at another way of doing Pauli exclusion. This is the conventional way of doing Pauli exclusion, antisymmetric wave functions. If I just do antisymmetric wave functions for 2 wave functions, and then I try to work it out using these objects, I suddenly find I'm left with P2 cross P1, which is antisymmetric, certainly, but it's also the only information that's there, the only information that separates the 1 fermion and the 2 fermion is the direction of the spin component. Not even the magnitude. The magnitude doesn't matter at all. It's only the direction. That's the only reason why it's not 0, is the direction of those things. So, we have any nilpotent wave function, that's any fermion wave function, would have a vector in real space at a different orientation to any other. And you could, one way of thinking of this is using projective geometry, just draw a plane perpendicular to each direction and all the planes will have to intersect. So we can define the uniqueness of a fermion either using the red coordinates or the blue ones. And the directions of the vectors in each space will carry all the information. It's interchangeable. Let me show you, like so. The first one, I didn't have the colours on this diagram. Well, that's the blue space on the left. That's the red one on the right. That's antisymmetric wave functions, that's nilpotency. So we can actually get the whole information in either of the 2 spaces. So these are truly dual, though they look different. I shall leave all that. Now let's try and represent particles by their charge structures, because each particle will have a structure of charge, how much weak, how much strong, how much electric. These can be done in 2 separate spaces. Let's look at baryons. and try ordinary space. It's obvious that baryons have some kind of rotation in ordinary space, and that determines their structure. How can we do that? I'm going to skip some of this because I'm now going to say, let's try and write down a three-component wave function, so a baryon. We can't write that because it's immediately zero, but we can write that. And I've been able to show that this must be what it looks like. And it's got solutions for 6 states or combinations of 6 states. You can have all the momentum or angular momentum in this one, or in that one, or in that one. Or you can have a combination of all 3. So there are 6 separate states, plus and minus. And that corresponds to the colour description, like so. And colour transitions, if you like, are transitions between those possible states, like so. You see, I'm just writing down the ones that I've got. There's no, it's all in the second one on this one. And you can make those correspond to the colour transitions. Gluons, of course, you can do the same way. And I will not go into any detail about that because it's too complicated. So the simultaneous existence of all the phases, those 6 possible phases, means that individual quarks are not identifiable space positions, even though we can define them in terms of space positions. So SU3 requires the rotation to be independent of the coordinate system used. Now, it's possible to show that this leads to an exact solution for the strong interaction. I don't want to go into detail about that, I'll just flash it through because it's not my main point. Essentially, if you've got a non-local connection between 6 phases, non-local means not dependent on position. The rate of change of momentum does not depend on position. In other words, it's, if you like, in mechanics terms, it's a constant force. A constant force is the same as a linear potential. Here we have to have a linear potential, potential proportional to distance. We also have a Coulomb potential for the pure symmetry. All the forces have, to define a point, have to have a Coulomb potential. So I'm not going to go into detail about this, but if I set up the version of Dirac equation using polar coordinates, hence the second term's changed into polar coordinates, the first term with the 2 potentials, I can actually get something like this out, and I get a phase term that comes out like this. And the first term in K dominates our high energies, approximating the free Fermion solution, asymptotic freedom. The second term has a confining potential dominating at low energies, infrared slavery. So we can get the correct solution. And nobody else has actually got an analytic solution for this, to my knowledge. Now, what I'm really interested in here is not that, though that is very interesting. I'm interested in how this affects the charge, because I've still not gone on to that. So this expression here has got an obvious spatial 3-dimensionality. How does that 3-dimensionality fit in with the charge 3-dimensionality? Well, we can recall that the 4 components in the Dirac spinner, the 4-component wave function for the Dirac, can be seen to represent the Fermis in terms of, if you like, unchanged gravity or inertia, then strong and weak electric vacuum. The 3 momentum components are mapped onto the space created by the 3 charges. This is the connection, and that's how you could do it. That's 2 different ways in which you could do it. There are other ways. We could use a phasor diagram, which is a neat way of doing it. And we have our 3. You see, we'll have our electric vector has to be on a different one to the W to give us those charge structures I showed you a moment ago, whereas on the lepton they can be on the same one. Now once these are on 2, then 2 dimensions always means 3, so we've got our 3 colour dimensions for the strong interaction. So we need an electric vector as well as a weak vector to do it. And that's how we would do mesons, same concept. If the strong charge isn't absent, we see they all line up. If the strong charge is present, to get the three components, we've got to spread them out. We can't spread them out unless we get the three component. Now I have to be somewhat heretical here since we talked about being heretical. I don't think this is very heretical, it's only slightly heretical. But to me, this gives this picture, which was first presented in 1964 by the Nobel Prize winner Nambu, Yokiri Nambu and Han. This seems to me to be a better picture than the conventional thirds and two-thirds. It is the same, it's not different, it's just a different way of representing it. We represent 2 electric for the up and -1 for the down. And what you get is you get the fractional nature of the charge comes obviously because the strong interaction is gauge invariant. So we cannot fix a phase. What we would have to do this properly is to write down all 6 phases at once. And when you write down all 6 phases at once, it becomes the same as if you'd written fractional charges down.
Don't you have to have a -2 E?
No, not for down. Down is -1. If you do a proton this way, up, down, plus E, minus E is 1. A neutron, down, up is, will work out as 0. You've got to do it. Yeah, that's the only way of doing it. If you divide this, if you average this out, that's 2/3, that's 2/3, that's 2/3. This is -1/3. I'll show you later. And we get exactly the same fractionalization of the electric charge anyway. We've observed it. We have actually observed fractionalization of the electric charge in the quantum Hall effect. There isn't the strong interaction telling you that it must be fractionalized, it's the weak interaction. Because in the quantum Hall effect, we trap an electron onto a series of magnetic flux lines. And if we have 3 magnetic flux lines, we get 1/3 of the charge in each, and we actually observe that. So there's nothing unusual about doing that. It's completely standard. So, I've studied this quark model, which is as old as the conventional quark model, but it used to be accepted as completely equivalent, but nobody talks about it anymore for whatever reason. Because in all observational terms, they work out exactly identical. They're just different ways of representing the same information. But I find it more valuable in many ways. So, that's my heretical bit at the end, but what I hope I've given some idea of is that the charges have a 3-dimensionality which is parallel to the 3-dimensionality of space, gives the same information, but you have to pull it out in a different way. And always in nature, because we have to have this zero totality, this balance, this non-characterization of nature, this non-bias in nature, we always have to get anything that we do in our space will be reflected in some process in the vacuum. And finding out what that is can lead to a lot of new information about physics. And I think we can also use the same type of things at a higher level, because I think the same process occurs at higher levels. Okay, thank you.
Thank you, Professor Peter Rowlands. Now we ask.
Okay, very initial talk. So I agree with you. Most of the normal life, normal particles are fermions,
Yeah.
but boson exist. And moreover, there are special conditions where you can change the way the fermions and the bosons, like explaining superconductivity.
Yes.
So we have some special idea about such point, or it's okay, everything we know?
I've actually got paired. Yeah. In my view, all gauge bosons and most other bosons are made by interactions of fermions or combinations of fermions. You can mathematically represent any boson in terms of fermion and antifermion. But you were talking about superconductivity, and there you've got the paired fermion structure. And I've had it here somewhere. I have the paired fermion structure. There we are. I think that's it. See the third one down there, paired fermion structure. Here you've got, instead of minus E, which is characteristic of an antifermion, you've got plus E. But you still get a scalar quantity because you've got plus and minus P.
I'm interested in your notion of a point coming about through two spaces interacting.
Yeah.
And geometrically, I think you can think about it in the following way. Consider two lines in a plane, let's say, and they produce a point if they intersect transversely. So if you think about image, then you can think about it and ask about the resulting higher dimensional space that's produced. So for example, two planes intersect in a point in 4 space. So that's a point in space-time or an event. And in your case, you have 2 3 spaces that are producing a point, and so there's a 6-dimensional space. So the question is the interpretation of the higher dimensional spaces that come out of that way of thinking about the production of a point in your context.
Okay. Yeah. Well, so I can use that one. Yeah. The point in this way of thinking is the zero norm that the nilpotent structure, which is constructed from the 6-fold space, has. So it's in that 6-fold space or higher space that you get zero totality when you square it, so you get a norm 0, and I think that's the way I look at the point in this structure. But I don't believe that if we didn't have particles of matter, we wouldn't be able to talk about point, because space is translation symmetric, and we can't pin anything down. The only way of pinning anything down is by something else.
Right, but then your picture of 2 spaces interacting, then they can.
Generically they can.
Generically,
yes.
Find a point.
Yes.
Through their transversal.
I'm saying there's no way we can get a point otherwise, unless we have something like that.
Another quasi-geometrical question. The quark string, you pull 2 quarks apart,
Yep.
and then the energy gets high enough, and quarks are produced in between them. I think you can hear me.
Yeah.
And so then the question is, how does the quark string and that production of quarks between quarks appear in your picture?
Well, I've said about the linear potential, which is what the quark string is about. So if you add in the quantum mechanics of things, where you can generate particles and antiparticles in the vacuum in addition, then putting those 2 things together will give that picture. And I've shown how you get the gluons as well.
But on the algebra side, it's as though you had a string of algebra elements. You have a couple of algebra elements.
Yeah.
You start pulling the algebra elements apart, and algebra is appearing between them.
Yeah.
Right?
It would be like that.
So you would also have a picture on that level.
Yeah. It always totals to 0, whatever you do. So you can always do that. Who's next?
Next is you. I have a comment. One comment, you have said that mass is a fundamental scalar quantity in physics.
Yeah, I mean energy as well. I mean energy as well.
Energy as well, but in my understanding of mainstream physics, mass as well as energy is a dynamical process. If you look at the Higgs model, it is a dynamical process which causes inertia. And that is something different in my understanding than in fundamental quantity. There is one point, perhaps I can add the section immediately. You have said that leptons are only subject to electric force, is that right?
No, I said they can be or not, as they choose.
Yeah, okay.
Some leptons are, some aren't.
Yeah, but okay, the other thing, you have said not to the strong interaction, but it was shown experimentally at Daisy Hamburg 22 to 24 in that range, that also the electrons are subject to strong interaction.
Oh yeah, they can split up into particles that are, because any particle can do that with high enough energy. You can make any particle subject to any interaction because you produce high enough energy for it to split up.
You mean the electron splits up into...
Well, the electrons and anti-electrons can together produce strongly interacting particles, yes.
Why?
Well, because they get enough energy. If it gets over the energy threshold needed, it can do it. But I'm talking about the more stable set of the particles, the more stable state of the particles. But you can make anything into vacuum energy, which can then become anything else.
Yeah, but it was understood in this experiment that this was a new thing, and it was tried to have a lot of explanations. For instance, the new exchange particle leptoquark to mediate between strong and electric interaction. But these particles have never been found. So the conclusion is that standard electron is also subject, very weakly, but still also subject to...
Certainly.
Strong
It doesn't have any strong interacting charge, but if you put electrons or any particles to high enough energy and they collide, they can produce anything whatsoever, as long as they're above the energy threshold.
I have some problems with understanding a point particle, because point is the volume of this particle is 0. When you have, for instance, an electron has a mass. When you divide this by 0, the density of the mass is infinite.
Yes.
When the charge of electron is divided by 0, the density of the charge is infinite. But you say at the end of your lecture that charges are two-dimensional, if I have good.
Yeah, well no, there are 3 dimensions of charge. I didn't say the electric charge is 3-dimensional. I said you've got 3 axes on which you can put your charges. But as for a point particle, well, it's just that the standard understanding of experiments so far is that the electron has never been seen to have any size, and they get it smaller and smaller and smaller. That's experimental, but I'm defining the point as the crossover between 2 spaces, not so much a point in a single space.
When you have 2 electrons and approach the electron to the...
It's a problem that nobody knows how to solve. But if you look at the Higgs field is the same value of energy at every point in space. That must be infinite density as well.
When you approach these 2 electrons to the length of Stone's length, then the force between these 2 particles is Planck's force,
Yeah.
10 to 45 newtons.
At that point, you can't actually measure the size because you then run into uncertainty principle and so on. You can no longer actually measure the size. But as far as you can go, electrons, nobody's got to the Planck length, it's a long way off. But they got to 10 to the minus 22 meters or something, and they still can't find structure in the electron.
And third, Einstein, when he used vacuum, he said that it's better to say plenum. On 1930, Einstein has a lecture at the beginning of the International Congress of the Sources of Energy. And in his lecture, he wanted to convince that the greatest source of energy is space-time. So also when he said we can on a sheet of paper with a bell pen write equations and show that the whole universe can be put in a 0 volume, but Einstein said in this case my theory does not describe the reality. These are singularities that do not describe the reality.
Yeah, well, Einstein he said that you can't have matter without space and time and vice versa. And I've said the same, because it has to be bundled into one package. You cannot define space and time without also defining this other space, if you like, which contains the matter and stuff like that. And so, I'm totally in agreement with that.
Thank you.
Okay.
I heard your last lecture at the last conference, and I've got the book, and I think you have the most elegant summary packaging of all of physics. It's wonderful.
Thank you.
And in reading it, I find myself feeling like a Neanderthal. How do I imagine your nilpotent? I can't imagine. I can't imagine what space, time, and charge, and so on means in maybe more layman terms. But would you try to address those issues?
Yeah, well, what I say about this is that if we want to get to the most deep level, it has to be abstract. If we've still got something that is familiar to us, like table or something, then we're not at the deepest level, because at some point nature has to go beyond our conceivable way of appreciating things. And so we have to do it in an abstract way. What I say is that we think solidity is a real thing because we experience it every day, but of course it isn't. If matter is made of points, then there's nothing solid, and then there's nothing that's more real than anything else. And so we have to, at that level, turn totally to abstraction. And I think if we don't, then we won't get to the most fundamental level.
But aren't those abstractions then part of us?
Yes, we're made of them. And the very fact that we can think of them, I think is in fact, they are part of us. We've had space and time for millennia.
So you're discovering us.
We're nilpotent, we're made out of nothing.
Yeah. But we've got abstractions. We've had space and time for millennia. And now we find we need at least two others. And possibly probably no more than that. And if we can do that, then we can package it. It's only like adding more to space and time. I'm just saying that let's get out of this idea that there's some reality in the real. I think Sydney, yeah.
I just wanted to ask you, can you state conclusively again why quarks should have electronic charge?
Why should have electric charge? Essentially, we cannot discuss space as a three-dimensional quantity without having another three-dimensional quantity in vacuum which will counter it. So anything that goes for space has to in some way go for charge. And so there's got to be a kind of mirror image of it somewhere else, even if it's distorted. And so we have to have another three-dimensionality.
When you had that picture of, this is the last question, when you had that picture of one of the slides, you had the E, you had the up, down, and it was the chart that showed E, minus E, and then 0. Was that part of one of the components? Electric charge? Like if you look at that.
Sorry, how do I get this? If I keep going down, it's down here.
That one. Yeah, that one. So these quarks, all three of them, or all two of them, are you showing in each of these blue, green, red components the, can you explain that a little bit more?
I mean, this is an old theory, it's 50 years old.
Okay.
It's not my theory, it's Ham-Nambu theory, but it was accepted for a long time as being equivalent to the standard quark theory, but it's just sort of dropped out without being disproved, it's just sort of dropped out of fashion. But What do you want me to explain on it?
Were you showing that this is the non-fractional version?
Yeah, well, it is the fractional version. It's just doing the fractional version in a different way, saying the fractions come from gauge invariance. The fact that we've got 6 of these at once, 6 tables like that, and we cannot tell one table from the other. So the only thing we see is the overall picture, which will be fractional. So it is the fractional version, it's just doing it in a different way.
Okay, thank you.
This is just one question.
But, by the way, what you asked me before, let's take the proton. It's got to have different colours. So let's take the proton. It can be any of those. So we can do blue and green for the odd and down for the red, and we'll get 1 for the electric charge, which is proton. If we take the neutron, we can, for example, take the red minus E, the green. Where are we? No, it's 2 downs, so we have to take another down, so the next down must be 0, and then we have an up which is E, so the total is 0.
You said there are 5 independent dimensions, 3 spatial and 2 of your IJK.
So they're not independent.
Well, so, let me just ask you this. Can you construct the SU5 or flipped U5 version of ground unified theory out of what you've done?
Yeah, I've got a kind of SU5 version.
Yes.
Exactly. I have an SU5 version, and by the way, I get grand unification of the Planck mass with it.
You get what?
Grand unification of the Planck mass with it. And but what I don't believe is what is normally done in grand unification is they don't have, instead of having the 3 interactions, they have a mixed electron weak and strong, and I think that's nonsense. It should be electric, strong and weak. If you do that, you use these, you get, I think you get grand unification of the Planck mass.
Last question.
I wanted to. Is it working? Yeah. I wanted to address 2 questions ago. The question of use from your start, where does our intuitive space come in? And I think it helps to think a little bit about the starting point, because you are starting at the point of symbol.
Yeah.
And as Brian was mentioning, you can think of symbol as the nexus of mind-matter, our space and matter. And so you start with symbol. It looks like you're starting in an extremely abstract position, but symbol quickly exfoliates into many things which are associated in a discrete way with spatial ideas. And you use some of them, and you take the opportunity to use them when you make calculations. By the time you get to the Dirac equation, for example, you're quite willing to take the quaternionic symbols and put an e to the I something or other and differentiate it and use continuous space. You're quite willing to go back and forth, and that willingness is actually a hint about how to think about the relationship between space and the discrete in general and in this particular theory.
Yeah, I think that is true, yes. If we look at what I said earlier, I think I was saying that we can do this ontologically or epistemologically. We can talk about space, time, mass and charge like that. I'm not sure where I've done that, but you can look at it. One of the ways I did it early on was to start with space as the only thing that you could measure or observe, and then look at what nature needed to do to balance that. So we invent the space, as it were, and then nature invents its own things to stop us describing nature in that way. And that's one way of looking at it. So that's our interaction then, and that you can do it in that format as well.
I think of this in terms of contextual interaction. Sometimes people start with a discrete theory, and then they say, well, we have to take a limit of the mesh and find out how the space arises and things like that. And you get hard problems coming out. On the other hand, another example of a different thing is take the complete graph on 7 vertices.
Yeah.
I say there's a knot in there. Where? It's nowhere, right? The graph is abstract. But there's a theorem that says if you try to put it into space, there will be a knot in it. Right. And it has to do with what kind of context will you clothe this with, and what happens when you do that, and you're free. You're free to examine those kind of contextual interactions.
Yeah, I mean, I have actually explored epistemology, ontology. Epistemology, ontology as part of the whole structure. And I think you can do it in different ways that way. It's just as long as you've got some sort of way of preventing you saying, oh, nature is this, it's totally discrete. When you do that, you meet with disaster. And sometimes the way I've presented this is saying that this is the only way you can get anything to work. You've got to take on board, you put in your input, and then nature puts its input back to you, and the total is what you use. Yeah. So there is that connection as well.
I think that other question can be put at the coffee break or at lunch. Thank you very much, Professor Peter Rowlands.